Welcome to today's class. Before we start on fluid mechanics, there is a small point carried over from the last class. So, in the last class we were discussing the following situation. There is a big massive object over here, and there is a smaller object which is falling, which is in the gravitational field of this massive object, and the small object we are assuming is gravitationally bound. And the question that we were addressing is, how close can the small object get to this big massive object before the tidal force produced by this disrupts this small guy over here. And we had found that the closest distance is capital R, which is given by twice the ratio of the masses. This is the mass of the big object, this is the mass of the smaller object, this to the power 1/3 into the size of the smaller object. In the last class I had forgotten to put this to the power 1/3. Okay. So, if this object gets any closer than this, it will be tidally disrupted by the gravitational field of this big massive object. Okay, this is tidal disruption. Now, in today's class we are going to discuss a little bit of fluid mechanics, and let me tell you why we are going to discuss fluid mechanics. Take for example the sun. The sun we know is a spherical, nearly spherical ball of gas, and if you want to study the structure of the sun, one describes it as a fluid. So, it is a gas which can flow under, if there is a pressure gradient, then the gas can flow. Okay. So, this the simplest possible approximation is to describe it as a fluid. Okay. So, there are various components in the universe which are conveniently described as fluids, okay, which is the reason why we are going to discuss a little bit of fluid mechanics. It is a tool, a theoretical tool that is extensively used in astrophysics and cosmology. Okay. So, okay, so what is the thing that we are trying to describe? You can well take water as an example. There is water, and we know that water is made up, any substance is made up of atoms and molecules. So, there really are, if you look at very closely water or any substance for that matter, there are particles, right, and one can write down the Newton's laws of motion for these individual particles. Or if you have a gas, we know that there are particles, and one can write down the Newton's laws of motion for these individual particles. But for many purposes, we are not interested in the motion of the individual particles. We are interested, it is more convenient to think of it as some kind of a continuum. Okay. So, when we think of water, it is convenient to think of it as something which is continuous. The discrete nature of the particle nature is not very important for many situations. Okay. So, we are going to, this is what we mean when we do fluid mechanics, we treat water or any gas as a continuum. It is something which is continuous, and we shall use then a macroscopic description of the substance that we are dealing with. So, we shall deal with quantities. So, let us just draw a picture. For example, this is a region of space which is filled with some medium, okay, and we will describe it in terms of the density rho. This is the mass density, so the density tells us the amount, the mass inside a small volume. So, if I take a small volume here, the density tells us the mass in this small volume. That is one of the things that we use to describe any fluid. Okay. It is a macroscopic quantity. If you look at it microscopically, you will find that there are discrete particles located. okay, but we are going to average the mass and use the density to describe it. Similarly, we will also use the velocity. Okay. So, we will ascribe one velocity to this region of the water in this region, that is the mean velocity of all the particles, water particles in that region. Okay. So, this is the other thing that, okay, the other quantity, other macroscopic quantity in this fluid picture. So, that is the velocity. And then we have the pressure, and we have the temperature. These are all thermodynamic quantities. Okay. And we know that the density, pressure and temperature are related through an equation of state. So, they are not all independent, right. There is, so if you know the equation of state, for example, for a gas we know the equation of state for an ideal gas. These are all not independent, they are related through some equation of state. So, we shall be dealing with these quantities. So, the entire state of the fluid is described by telling its density, its velocity, pressure, temperature, actually any two of them will do, at all points. Okay. So, this is how we describe this in a macroscopic fashion. So, we shall deal with these variables, that is the first thing. Okay. So, this is the macroscopic picture. The second point is that there are two approaches to fluid mechanics. The first approach is called Eulerian approach. The Eulerian approach. Okay. So, in this approach we look at the fluid at a fixed point in space. Okay. And we consider whatever, so when we want to study the density, for example, we will focus our attention in the Eulerian approach at the value of the density at a fixed r. So, r will remain fixed, and if the fluid flows, then different elements of the fluid will come to this r at different times. Okay. So, say the fluid flows like this, okay, and I look at it at two different instants of time at a fixed r, then I can ask what is, how does the density change. So, we have del rho del t, which is at a fixed r. Okay. So, r is fixed position, fixed position. Okay. This is rho at r plus r comma t plus delta t minus rho at r comma t, the whole thing divided by delta t, right. So, we can look at the derivatives and things like that in this Eulerian picture, and when you evaluate this derivative, you are essentially looking at two different bits of fluid, because the fluid is flowing. So, if I sit here, I will see that different parts, the fluid that is flowing past me. So, if I look at it one instant and I look at it the next instant, a different fluid element will be here. The one I was looking at in the past would have shifted somewhere else. Okay, this is the Eulerian picture. We also have the Lagrangian picture, the Lagrangian approach. And in this approach, what we do is we follow a fluid element as a single fluid element as it flows. So, here suppose I am looking at the density, then I will follow this fluid element as it flows. So, if it moves from here to here, I will follow this. So, my attention here is on a particular fluid element. Okay. And we have something called the convective derivative here. So, when I look at so, if I ask what is the time rate of change of density in the Lagrangian picture, I do not sit at a fixed place and look at the fluid flowing past me. I move with the fluid and then ask the question. Okay. So, I follow one piece of the fluid as it flows from here to here and ask how does its density change. Okay. And there will be a change here due to two reasons. So, the position also will change, and the change in the position is r plus v delta t into t, and here t plus delta t minus rho r t. Right. So, that is the convective derivative, and if you do a Taylor expansion in this delta t, you will have two terms. The first term will be del rho del t, it is the partial derivative at a fixed r, that will be one term, and there will be one more term which is v dot grad rho, right. That, so, the spatial variation in rho at a fixed time will also come in because the r has changed. Okay. So, if I write this in terms of partial derivatives, I will get two terms. One is the partial derivative of rho with respect to time, and the other is v dot grad v dot this term the gradient of rho. Okay, this is called the convective derivative, and it is a derivative. So, this tells you the rate of change of the density or any quantity for that matter if you move along with the fluid. Okay. So, these are the two pictures. Now, let us determine the equations that govern fluid motion, the flow of a fluid. So, the first, these equations, the first, all of the equations that we are going to consider, they are essentially guided by conservation principles, okay, something like conservation principles. So, let us first consider the mass continuity equation. Okay. Or it is called just the continuity equation. And the way we arrive at this equation is as follows. Consider an arbitrary volume like this, okay, and let us ask the question, what is the mass inside this volume? Now, that is straightforward to calculate. The mass is the density. So, the mass in this volume m is the integral of the density over the volume, right. This will give me the mass. Now, let us write the rate of change of mass. And the rate of change of mass, if I differentiate this with respect to time, the volume remains fixed. I am working in the Eulerian picture, so the volume remains fixed. The mass in this volume can change only because of the change in the density, right, because the mass is the integral of the density. So, the mass, the rate of change of the mass will be del rho del T dV, where the integral is over this volume. Okay. Now, we know that mass is conserved. So, the mass, if any mass changes inside this volume, it could occur either because the mass has flown out or mass has flown in. Okay. So, this will be equal to, now if the mass flows out, then there is a net flux of the mass which is positive. So, this is going to be equal to minus the mass flow out from this volume. Now, the mass is going to flow out of this volume through this surface, okay, and the mass that flows out, the rate at which the mass flows out is given by the surface integral of ds, that is the surface element area pointed like this, dot j, right. This is a general kind of thing, and the flow. So, the rate at which the mass flows out is the surface integral of the mass current. J is the mass current, that is the rate at which the mass is flowing per unit area. By current we mean the rate at which it is flowing per unit area, right, and if I divide this over the integrate over the entire area, I will get the total mass rate flowing out. So, the rate at which the mass changes is minus this, because any mass flows out, the total mass will come down. Okay. Now, how much is the mass current? The mass current, or for that matter any current, is the quantity into the velocity with which it flows. Okay. Right. So, if I want to calculate the mass current J will be the mass density rho, mass per unit volume, into the velocity with which it is flowing, right. So, now if I take a unit area and ask the question how much mass is crossing it per unit second, it will be given by J dot the area, right. So, this is the mass current. Okay. Now, I can, so I have this over here. So, if I use this, okay, let me now do it in a more general term. So, this term, using Gauss law, we can write it as minus, now this is a surface integral that can be converted into the a volume integral of the divergence of this current. So, I can write it as del dot J dV okay. And if I now equate the left hand side with the right hand side, I have two volume integrals, one on the left hand side and the other on the right hand side, and these two should be equal. So, it tells me that the integrands should be equal. So, I am led to the equation del rho del T plus the divergence of the mass current, which is rho into the mass into the velocity, this should be equal to 0. So, this is the continuity equation. Okay, it tells me that matter is conserved locally. So, if the density goes down somewhere, that means that the matter is flowing out from there. Okay. We can look at it like this, this is a small unit volume, and if the density goes down over here, it tells me that there is a flux of matter flowing out. So, if this term is negative, then this term has to be positive. The divergence of the mass current is essentially a measure of the flux flowing out. Okay, that you can easily verify using from the Gauss theorem. Similarly, if the mass is increasing in this unit volume, then there should be a flux inwards. Okay, this is the continuity equation, and we can expand it and write it out also. So, let me do that here. So, if I expand it and write it out, then I have del rho del t plus, then I will have one term which is rho into divergence of V plus V dot gradient of rho, this should be equal to 0. Okay, so that is the continuity equation, the mass continuity equation. It tells us that matter is neither created nor destroyed locally. Okay. This is the first fluid equation. Let us now look at the, let me put down the equations over here in one place so that we have it for future reference. Okay, so the first fluid equation is del rho del t plus the divergence of the mass current is equal to 0. Okay, this is a continuity equation. Now, let us take up the next fluid equation. Next fluid equation is the conservation of momentum. Okay, so we have looked at the conservation of mass. Let us now look at the conservation of momentum. So, we can use the same picture. You have this volume, or let me, okay, we have this volume. Let us write down the momentum inside this volume, okay, total momentum. So, for simplicity, we will write down only the x component first, and then we can generalize it to all the components. Okay. So, let us take the x component of the momentum. So, the total momentum inside, momentum is mass into the velocity. I have to integrate mass into velocity. So, this is the momentum equation. And I am interested in the x component of the momentum, and this will be given by the integral of the mass rho, mass per unit volume, into the velocity of that volume in the x direction, which is of that mass in the x direction, which is Vx, into the integrated over the volume V, total volume. Okay, this is the velocity, this is the volume. Fine. So, that is the momentum in the x direction. Now, let us ask the question that what is the time rate of change of momentum in this volume p dot. So, p dot, let me draw this volume here, and that is my fluid. Okay, this is the x direction. So, P dot along the x direction will be again the time rate of change of rho into Vx integrated over the full volume. Okay. So, that is the rate of change of the momentum in this sphere along the rate of change of the x component of the momentum. Okay. Now, let us apply the law of conservation of momentum. The actually it is the second law of Newton's second law of motion. So, this momentum can change due to various reasons. Okay. So, the first reason is that the momentum can either flow in or flow out. Okay. So, what is the rate at which momentum flows out? Let us ask the question, what is the rate at which momentum flows out? So, again we have to do what, how do we calculate that? We have to calculate the momentum flux, momentum current. The surface integral of the momentum current will give us the rate at which the momentum flows out. So, we are interested in the x component of the momentum. So, how do you calculate the current? Just multiply it with the velocity. Okay. So, this will be equal to one term which is the integral ds dot the momentum current, and the momentum current, the mass current was rho into V. So, the momentum current is going to be rho into Vx, that is the x component of the momentum, into V. Right, rho into Vx is the quantity we are looking at, the rate at which it flows is rho into Vx into V, just like the mass density. If I ask the mass current, it is rho into V, the momentum current is the x component of the momentum into V. So, this is just the flow in or out of the momentum. Momentum can flow in, momentum can flow out. Okay, that is one of the possible reasons why the momentum can change. Now, there is another possibility. We know that is Newton's second law of motion, that the rate of change of momentum is equal to force. So, we have to calculate the total force acting on this fluid. Now, there can be two kinds of forces. One is called a body force. A body force acts all through the fluid. Okay. So, let us assume that there is a body force and the force per unit mass, we will call it small f. Okay. So, force per unit mass is small f. So, if I want to calculate the total force, the rate of change of momentum will have a term which is plus the total force is the force per unit mass, which I am calling small f, into the mass, which is per unit volume, which is rho, integrate over the entire volume, which is dV. Right. If I do this integral over the entire volume, I will get the total, and I am only interested in the x component of the force, so I will write Fx. Okay. So, F is the force per unit area, per unit mass. F is the force, small f is the force per unit mass, which we also call acceleration, right, and it is acting on the entire fluid. And so, this is the force per unit mass, this is the mass per unit volume. So, this gives me the force per unit volume. I integrate over the entire volume, I will get the total force acting on this fluid. Okay. And I am only interested in the x component, so I have taken Fx. That is the next term. And we have one more term which is possibility, which is a surface force. Okay. So, there may be forces acting, external forces acting on the surface of this fluid. So, we could have forces which act on the surface. So, we could have surface forces here. They act on the surface, and we are going to consider a particular kind of a surface force. So, let me write these terms over here. Okay. Let me not, so F, what these terms are. So, F is force per unit mass. Okay, it is a body force. and we will consider a particular type of surface force which is pressure P. So, if this surface is immersed in a fluid, we know that there will be pressure exerted by the fluid outside on this, and we know Pascal's law, Pascalian. So, this is called Pascalian pressure, right. So, Pascal's law, which says that the pressure is isotropic, same in all directions. Okay. So, if I put a surface over here, if I take this surface, the force due to the pressure is going to be normal to the surface. So, the force due to the pressure is going to act in the same direction as ds, the unit surface, the surface area. Okay. So, if I want to calculate the total external force due to the pressure, I am interested only in the x component of that, only in the x component of that. So, then I can write that term as there being one more pressure, one more force term, which is the integral of pressure into the x component of the surface area, because the pressure is always along the surface area and we are interested only in the x component of the force. Okay. So, I will write this as I, that is the unit vector along the x direction, dot ds. Okay. And this will have a negative sign because the pressure acts inwards, opposite to the surface area, right. So, I have P dot, which is equal to this plus this plus this, there are 3 terms. Now, again P dot, we have a volume integral here when I write it in terms of the rho into V. This term is a surface integral which we can convert into a volume integral. This term is a surface integral which we can convert into a volume integral. So, let me write down the final equation, and the final equation is going to be, so first we have this term here. So, the integrands of all the volume terms, integrals should be same. So, we have del by del t of rho Vx, that is this, is equal to minus the divergence of this term, right. So, this will be equal to minus the divergence of rho Vx into V, right. That is the divergence of this term, and then I get a volume integral, that is Gauss law, and here I already have a volume integral. So, what I have is plus rho into Fx, and then I have to take the divergence of this term, and the divergence of this term is going to be minus the divergence of P into I. So, this is the conservation of the x component of the momentum. Okay. Now, we can simplify this a little further. So, let me simplify it a little further. So, I will have the left hand side, let me do this simplification here, it is a bit of an algebra, but let us go through it. So, I will have 2 terms here, one term is del rho del t into Vx plus a second term which is rho into the partial derivative of Vx, and this is equal to, I can take this onto the onto the left hand side. So, I will have plus, again there will be two terms. One term is going to be the divergence of rho into V into this whole thing into Vx, and there will be another term which is plus rho into V dot the gradient of Vx, right. So, I have written this term taking it to the left hand side, and I have written it in as two terms. I have broken it up, okay, and I have this term. So, this is going to be equal to rho Fx, and look at this term now. This is the divergence of the pressure into I, the unit vector. When I take this divergence, there will only be a del del x term, partial derivative with respect to x. There will be no derivative with respect to y or z, because j and k do not appear over here. Okay. So, I will have one more term which is minus the x derivative of the pressure. Okay. Now, you see, we can simplify this. Look at this term, this is del rho del t, del rho del t. Del rho del t is equal to del rho del t plus the divergence of rho into V is 0. So, we can combine this term del rho del t, and here we have the divergence of rho into V, all of them, both of them multiply Vx. So, the sum of this and this is 0. Okay. And we are left with, let me write down the remaining terms. So, the remaining terms, we can cancel out rho throughout, rho occurs everywhere. So, we can cancel it out throughout except for this term where there will be a 1 by rho now. Okay. So, let me write down this equation. So, the equation is del Vx del t plus V dot the gradient acting on Vx. So, I have written this term, I have written this term is equal to Fx minus del by del x of P. Okay. This is only the x component of the momentum. I have similar equations for the y component and the z component of the momentum also. There will be a 1 by rho here. Thank you. Correct. So, there will be a 1 by rho here, right. So, there will be three such equations, one for the y component, one for the z component also, and I can now combine all three equations and get my final equation. So, let me write down the final equation which I get when I write. So, I can write this for a vector v. So, let me write down the final equation. The final equation is del v del t plus v dot grad v is equal to minus 1 by rho into grad p plus f. Okay. So, that is my final equation, and this is called the continuity equation, and this is called Euler's equation. Okay, Euler's equation, Euler equation. This is Euler equation. Okay, so this tells me what how the velocity will evolve. Okay, this tells me that the mass is conserved. Here we have used momentum conservation to calculate the evolution of the velocity. Okay. Now, there is a third equation which is the conservation of energy. So let us look at so we have looked at the conservation of mass, we have looked at the conservation of momentum. Let us next look at the conservation of energy. Okay. And so this is the energy conservation equation. Okay. Fine. Now here, so we start when we discuss the energy conservation equation, we start from the first law of thermodynamics. So let us consider some fluid element like this. This is my fluid element, and if I compress or rarefy this fluid element, stretch it, then we know that this is going to be governed by the energy exchange is going to be governed by the first law of thermodynamics, and the first law of thermodynamics tells us that dq is equal to du plus p dv, right. So the heat flow is equal to the internal change in the internal energy, the heat that this system exchanges that flows across the boundary of the system is equal to the internal energy, the change in the internal energy plus the work done. Okay, this is the first law of thermodynamics. It is essentially the conservation of energy. Okay, and we know that the entropy ds is defined as dq by T. Okay, so we can say that this is equal to T ds. Now in our discussion, the fluid element that we are looking at, not only can it get compressed or stretched out and exchange heat, but it can also flow. Okay. So we have to now consider this fluid element as it flows, as it moves. So it is, first of all, this thermodynamics, this law holds for a fixed system. My system cannot change. Okay. And since my system cannot change, it is obvious that I should look at this fluid mechanics not in the Eulerian picture, but in the Lagrangian picture. Okay. So it is very clear that we have to work in the Lagrangian picture. We have to follow the same fluid element as it flows. We cannot look at different, if we work in the Eulerian picture, then we will be considering different fluid elements at different time elements, right, at different instants of time. So it is clear that we have to first write down the equations in the Lagrangian framework. So we are following the evolution of one fluid element. That is the first thing. Second thing is, then let us consider a fluid element of unit mass. Okay. So we will work with the entropy per unit mass, sigma, right, and the rate of change of entropy per unit mass So my system has unit mass. The rate of change of entropy per unit mass is equal to, right, so we are considering, we are interested in the rate of change of entropy per unit mass, and that is going to be the heat. So T, we are interested in this, right. So T times the rate of change of entropy per unit mass is going to be equal to the rate at which heat flows in or flows out of this mass element. Okay. So this we can say is, we can write it like this. Okay, so sigma is entropy per unit mass, and L is the energy loss, is the heat loss per unit volume. So we would like to convert the heat loss to per unit volume to the heat loss per unit mass. This is the heat loss per unit mass, heat change, heat flow per unit mass. So we just divide it by the density. Density is mass per unit volume, and this will give you the heat loss rate per unit mass. And since it is the loss, we put a minus sign. Okay, and this tells you the heat gain, which is T dq. So I have essentially written this equation in this way for a unit mass and differentiated with respect to time. Okay. Now this can also be written, so we know, let me also introduce the internal energy. This is the internal energy per unit mass. So the conservation, the energy conservation can either be written like this, and if it's an adiabatic situation, then the right hand side will be 0, there will be no heat loss or gain if it's an adiabatic situation, and we have the fact that the energy entropy per unit mass is going to be conserved. Okay. In case it is exchanging heat, it's not adiabatic, then there will be a heat loss or heat gain which is given by this. Okay. We can also express this in terms of the internal energy per unit mass. So let me do that. So we know that T d sigma, so this will be written as, so we are going to use this expression now. So we have, first I am writing this in terms of these two. So I will have one term which is the rate of change of internal energy per unit mass. So I will have one term which is that is this term, and this is going to be pressure into the rate of change of volume per unit mass. Now the volume, so I will have one more term which is plus P into d by dt. Now the volume per unit mass is going to be 1 by the density, right? Density is mass per unit volume, so volume per unit mass is going to be 1 by the density. Okay. So the same equation now becomes this, and this is equal to minus the heat loss per unit mass. Okay. And this becomes okay. Now we can further simplify this term here. So let me just simplify this term. So this term can be written as 1 by minus 1 by rho square d rho dt right. I am just simplifying this term here, and this becomes equal to minus 1 by rho square Now this is the convective derivative d rho dt. I am following the same fluid element as it moves. So we can write this as del rho del t plus v dot grad rho which we can use the continuity equation. Look at the continuity equation. If I break this up, there will be one term which is v dot grad rho, and there will be one more term which is rho into divergence of v. So I can write this as 1 by rho square rho into divergence of v using the continuity equation. Okay, so I have just simplified this term over here. So now I can plug this back in here and multiply it throughout by rho, and what I get then at the end of the day is the following equation. I have rho into the convective derivative of the internal energy plus P into the divergence of V right. One of the rho cancels out from here and one of the rho cancels out when I multiply it with rho, is equal to minus the heat loss rate per unit volume. Okay, so that is the conservation of energy. So let me write it down here. This is energy. Finally, let me take up these are the three fluid equations. In addition to this, we shall be using quite often a fourth equation, and that is the fact that the force that we are dealing with is gravitational. Okay, so we have a gravitational force So the body force that we are dealing with, so if I have a fluid here in a gravitational field, then it will experience, any element of the fluid will experience an acceleration, force per unit mass, F, which can be written as minus grad of some potential phi. Phi is the gravitational potential. Okay, so for a gravitational field, gravitational force, we know that the acceleration can be written as minus grad of phi, where phi is the gravitational potential. Okay, that's the first thing. Now, second thing is, given the mass distribution, the same mass distribution, it's going to produce a gravitational field. So I am interested, let us say, in calculating the gravitational field produced by this at some point r over here. So I am interested in calculating phi at some point r. How do I calculate, produced by this mass, how do I calculate it? So I have to, what we do is we divide this up into small mass elements. So let us ask the question, how much is the gravitational potential produced by this mass element at this point? So that we know that this will produce a gravitational potential here, which is minus g m by this distance. Okay. So, if I say that this is located at r prime, okay, then this is going to be minus g into rho at r prime d cube r prime, that is the volume element over there, divided by the distance between these two, which is r minus r prime. So, this tells me the gravitational potential produced at r by a particle at r prime, the mass of that particle being the density into the volume, okay, minus g m by r. And to find the gravitational potential by the entire object, I have to integrate this over the whole of space. Okay. So, this tells me the gravitational field produced by a mass distribution, and here we shall be dealing with self gravitating systems. So, the field acts back on the same object itself. Okay. So, it is an extended object and the field acts back on the same object itself. Now, without going through the calculation, it is a very simple thing. I shall just write down. So, this is the way you can calculate the gravitational potential from the mass density. It is convenient to write it instead of this integral expression, write it as a differential expression, and that differential expression can be obtained if I act with the Laplacian, if I calculate del square phi. So, I act with the Laplacian on this del square phi, and this comes out to be 4 pi g into rho r. Okay. So, this is the same equation as this, these are identical. So, if I take the Laplacian operator and act it on this phi, I will get this, okay. Or if I integrate this equation, I will get this as a solution, okay. And this equation is called the Poisson equation. No, there will be a positive sign. Del square phi is 4 pi g into rho. Okay. So, for a self gravitating fluid, in addition to the three fluid equations that we had, we also have the Poisson equation, which is del square phi is equal to 4 pi g rho. This is for a self gravitating fluid. So, the fluid exerts a gravitational force on itself, different parts of the fluid exert gravitational forces on the other parts. Okay. This is called the Poisson equation. This is essentially the Newton's law of gravity written in the form of a partial differential equation, nothing more than that. Okay. So, today let me stop here. Today we have introduced the fluid equations, and in future classes we shall apply these fluid equations to astrophysical situations.